so do Sunday narrative on neural signaling. Okay? If you have any questions, you can email me. We're going to get going. So, as John told us at the start, there are two systems for communication in the nervous system. There's electrical and there's chemical. Electrical is good to travel long distances. It's fast, but it's only an on-off signal. It's binary. You either have an electrical signal or you don't. Okay? And so we'll talk about synaptic potentials and action potentials today. Chemical signals are good because they can tell neurons different things. Because different chemicals can have different actions. They can be selective. They can do different things. That's the way your heart knows to speed up or slow down depending on what neurotransmitter is being released by the autonomic nervous system. Right? Norepinephrine has one effect. Acetylcholine has another. So signaling between neurons or between neurons and their target organs, right, is chemical. And electrical happens within the neuron. Within the neuron. All right, so this, while I was playing a lot of sports stuff this morning, because isn't it ionic? Not ironic, that's my bad joke for the day. We need to talk about ions, okay? And so here are some ions that we're going to be dealing a lot with. We have sodium, Na, potassium, chloride, calcium. What do you notice about those? What comes after their abbreviations? A charge, right? Ions, an ion is a molecule that has an electrical charge, either positive or negative, associated with it. A couple things we need to know about that, right, is, regardless of charge, ions respond to the laws of entropy. Does anyone know what that means? It's like our physics, chemistry lesson. Is it order? Order, yes. In particular, they want to be at equilibrium. Given the ability to go to equilibrium, they want to go to equilibrium. Okay? So, if they're concentrated in one area and not in another, they want to go so that they're at equal concentrations. A couple other things that are important to know. Opposites attract. Okay? So a positive charge is attracted to a negative charge. They balance each other out. So what table salt? What kind of molecule is table salt? NaCl. Yeah, NaCl. It's sodium chloride. So the positive of the sodium matches up with the negative of the chloride to become that molecule. All right? So opposites attract, and they want to go to equilibrium. Those are going to be two really important points for us today. All right, back to our three important components, right? Sodium selective and potassium selective. What does it mean that they're selective? When I say they're selective, what does that mean?
Only sodium molecule is only potassium molecules capacity.
Yes, it's selective for that type of molecule, but what else? So that's half of the story. Yes, Kevin? What's that?
Does it only go one way?
It only goes one way, yes. So sodium can only do what? Come in. Potassium can only do what? Go out, right? And then we have our sodium-potassium pump, which uses ATP energy. And which way is it moving the sodium and the potassium? It's right there. Sodium's getting pumped out, potassium's getting pumped in, right? Every ATP molecule, every piece of energy that it uses right? How many sodium go out and how many potassium come in?
Is it
You said that? Someone said it?
two?
Speak up.
Is it 3 sodium and 2 potassium?
3 sodium out, 2 potassium in. Absolutely. All right. So here's our fancy neuron, right? Our cell membrane, and I'm going to put my fancy little drawings of pumps, the pump and 2 channels. When we say a neuron's at rest, it means nothing's activating it. There's no neurotransmitter activating it. It's just sitting there, right? When that's happening, all the channels are closed, but the sodium-potassium pump is still working. So if the sodium-potassium pump's working, what does that mean? It's using ATP. And where is the sodium? Outside, because the pump is doing what? It's taking any sodium in here and putting it out here. Every time it's going around, round and round and round. So most of the sodium in red here is outside the neuron, and there's very little sodium inside the neuron. But what else is happening besides moving the sodium out? We're bringing potassium in. So most of the potassium is inside, and very little is outside the neuron, right? Now, is sodium happy about that? What do we say about the 2 things that are important about ions? They want to go to equilibrium, and opposites attract. We'll get to opposites attract in a minute, but right now with equilibrium, where does sodium want to be? Inside. Low concentration, high concentration. It wants to move inside the cell. Where does potassium want to be? Outside. It wants to get out of the cell. But it can't. There's no way to go through there because our channels are closed. Okay? All right. So this produces a force that wants to make sodium come in and potassium leave. That's the importance of the pump. The pump provides that concentration gradient, the difference, that is going to make sodium want to come in and make potassium want to leave. All right? In addition, remember those things that we said were trapped inside the cell, like the nucleus and the mitochondria and all that stuff? Those things tend to have a negative charge associated with them. And so that makes the inside of the neuron more negative than the outside of the neuron. Okay? So in addition to having a concentration gradient or force, there's also an electrical force. Right? So what charge is potassium? Positive. So it's more negative inside and opposites attract. Based on the electrical gradient, where does potassium want to be? Inside. It's happy inside electrically. Concentration-wise, it's like to leave. But electrically, it's like, I'm okay in here. What about sodium? What kind of charge does sodium have? So where does sodium want to be based on electricity? Inside, right? It's like, hey, let me in. It's crowded out here, and I like the electrical charge inside the neuron. All right? So this is another force that neurons have available to them to move these ions. Okay? And it happens to be that the difference between the inside and the outside of the cell is around negative 70 millivolts at rest. Negative 7. That's going to be an important number. We call that the resting potential, because it deals with voltages. Okay? All right, so is anyone an electrician in here? Trained electrician? No? Good. One of these days, someone in my class will be like, yeah, I used to do that in high school. And then I'll be in trouble, because I don't know a lot about electricity, but I think I know more than you, based on the fact that you're an electrician. So we need to talk a little bit about electricity. And sometimes electricity, it's kind of, we We almost treat it like it's magic. We don't really understand how it works, right? But if I ask you how plumbing works, you guys probably have a pretty good idea, right? You have pipes. What's in the pipe? Water, yes, right? And you have to have some water pressure in order to move the water. Like you turn on the faucet, if there's no water pressure, what happens? Nothing happens, right? There's water in the pipe, but it doesn't move. You have to have pressure in order to move it, right? So electricity is a lot like that. If you think about it in terms of plumbing terms, voltage is like pressure in plumbing, right? It's the force that moves current along a wire. Right? So voltage, when we talk about millivolts, we're talking about voltage. That's the force to move things. Some handy voltages to know. What is the voltage in this wall outlet right here? Does anyone know? It's different in Europe. No one really is an electrician. All right. So 120 volts. Okay? That's what's in a wall outlet. What kinds of things do we plug into wall outlets?
Lamps.
Microwaves,
Lamps.
lamps, what? Refrigerator, and someone said chargers, right? So on your charger, right, can you take your USB cord and plug it directly into the... No, Rachel, what would happen if you did that?
Isn't it? That's too much of a connected. There's something that has to be like a buffer between them.
Yes, because that's too much force.
Yeah.
120, so we need 120 because you need to power a vacuum cleaner with a big motor on it, or a refrigerator that has a compressor. So this is actually a lot of force, right? A lot of force there. So for something that's small and delicate, like a computer, a laptop, a phone, we have to have that block that's going to reduce the force and only let it trickle into your device so you don't blow it up, right? So, for instance, a Pentium chip in a laptop uses about 4 volts to move electricity through the computer. And that's why you can't plug it directly into the wall outlet. A AAA battery has about 1.5 volts, right? I have 2 in this little remote. I just had to replace it to make my little laser pointer and the receiver work. So this thing only needs 3 volts in order to power it. Right? A neuron over here has 70 millivolts. Millivolts. That's 0.07 volts. Right? Do y'all know this movie? It's like gold. When I first started teaching it, it's like, yeah.
Matrix.
The Matrix. What's the premise of the Matrix?
Computer learning some kind of weird.
Computers have taken over the world. What do they do with all the people?
They're using people as a power supply.
They're using people as batteries, right? It's an interesting science fiction premise, but not really efficient, right? Because you get 1.5 volts out of a AAA battery, but only 0.07 volts out of a person, right? So we're not very good batteries. We wouldn't be a very good power supply. We'd be doing a lot better just manufacturing batteries and using them as, okay? So we can have such a low voltage because we don't. The electricity doesn't have to go far before it's regenerated. Okay. So what would happen if I stuck my finger in the wall?
Nothing good.
Would that be a good thing or a bad thing?
Bad.
Why is it bad? Because we have 120 volts, that force, right? When we only need 0.07. Our body's built to handle 0.07, and there's 120 coming out of there, right? It'd be like trying to drink from a fire hose. You wouldn't want to do that. A lot more pressure than drinking from a garden hose, right? Okay. All right. So, I'm going to go through this real quick. Summary. Where's the sodium? It rests. Outside. Where does it want to go?
Inside.
Where's potassium?
Inside.
Where does it want to go?
Outside.
Outside because of what? Concentration, but electrically inside. So it's kind of like on the fence if it wants to leave or not. It's like I kind of want to leave because there's a lot of potassium, but it's negative, so that's kind of holding me in. Right? All right. So we have a concentration gradient that wants sodium to come in. See, coming in. This is sort of showing us it on one, but remember the two separate selective channels, right? Channels closed. Potassium wants to leave, right? The voltage difference is -70, so electrically, sodium wants to come in, but electrically, potassium wants to stay in, right? And actually, any potassium that's out here kind of wants to come in based on the electrical charge. Okay? All right, we're good? Awesome. All right. This is figure 1.5 in your book. There's some things wrong with this figure. I'm not real happy with this figure. One of the things that's wrong is that they're showing this pump kind of like it's a channel, but it's not. It's a pump. And it uses energy, right? It's not showing that. It's also showing that the channels are open when the neuron's at rest, but they're not. They're closed. Like the sodium channel's closed, but the potassium channel's open. They're also showing us a potassium channel that lets potassium come inside, but that's not what happens. It only goes outside. So I've shown this to you so you don't get confused. Sort of ignore this figure in the book if you will. Yes, Logan?
I was trying to write it out as we were saying it, but I got a little confused. So sodium is out, but it wants to go inside.
Yep.
And then potassium, I can't remember if we said it was, is it out too, but wants to come inside?
Concentration-wise, it wants to leave, right? But electrically, it wants to stay inside because it's more negative inside the cell.
Okay, so it wants to leave concentration.
Mm-hmm. All right, we're getting there. We're getting there, people. All right. You remember last time we said that neurons do 4 things. Input happens where?
Dendrites.
Dendrites. What's next?
The axon.
Soma. Soma does processing, right? Makes a decision about sending an output, yes or no. Axon, signal conduction. Output. Release the neurotransmitters happens at the axon terminal. Okay? All neurons do these 4 tasks, even though some may be specialized. Okay? All right, how do we know the stuff I'm about to talk to you about? Well, we can actually take a neuron, like a cultured neuron in a dish, we talked about that as a preparation, and do electrical recordings from it. We can stick an electrode inside the cell because the cell membrane is what? Is it a wall like this? It's like plasma. It's a plasma membrane. So we can carefully stick an electrode in there and not destroy the cell and measure the electrical charge inside. You have another electrode outside, and guess what? When nothing's happening, this electrode is negative 70 millivolts more negative than this one. Right? We can actually measure this. Okay. And we do that one of our so I like it. All right, gotta get move. We're going to break this into 2 different processes: synaptic potentials that are going to happen in the dendrites and soma, action potentials that are going to happen in the axon and axon terminals. So we're going to talk about input and processing first. There's going to be some important things there, right? So we're going to talk about neurotransmitter or NT-gated channels. Means that neurotransmitter is what opens the gate. Okay? Talk about EPSPs, IPSPs, and summation. Okay? So we have neurotransmitters that are the chemical signal interacting with the dendrites. That signal then is going to get taken to the soma, a decision made, and then we'll talk about transmission and neurotransmitter release. So focusing on the first two first, okay, synaptic potentials. So we're going to have neurotransmitters coming from other neurons that are the inputs, and we get these little blips down here of increases or decreases in the electrical potential. How does that happen? Well, we can have these positive increases are called EPSPs, excitatory, postsynaptic, on the postsynaptic. So when we have two neurons, talk about we have a chain of neurons, right? This is the pre, and this is the post-synaptic side. So postsynaptic potentials. And so that sodium channel that we said is closed, it can be opened by neurotransmitters. So a neurotransmitter comes along and opens that channel, and what do you think is going to happen? Where does sodium want to go? Inside the cell. And what kind of a charge does sodium have? So if we let some sodium inside the cell, what happens to the inside of the cell? Gets more positive, right? All right. The neurotransmitter only bonds for a short period of time, and then it lets go. Well, we let some sodium in and we got more positive. The neurotransmitter leaves. Why don't we stay positive? The gate's closed when we let sodium in, so why didn't it just stay up here?
Because potassium goes out.
No. What's happening when there's nothing going on, when no channels are being activated? What's going on in the neuron? The sodium potassium pump's still working. So we let the sodium in and the pump says, hey, get out of here. And it pumps it back out when we go back down to resting potential. Alright? So it only happens for a brief period of time. We also can have it get more negative, inhibitory postsynaptic potential, IPSP. That happens with potassium. So if a neurotransmitter comes along and activates a potassium channel, that potassium, because of the concentration gradient, is going to leave. If potassium leaves, what kind of a charge does potassium have? Positive. So if it leaves, what happens to the inside of the cell? Gets more negative. That's how it's inhibitory. There's another important neurotransmitter-gated channel that's a chloride channel. And I'm going to tell you it produces this. So what does that mean happens when the chloride channel opens? It comes in, and it has a negative charge. That's how it inhibits. All right, so 3 important transmitter-gated channels. Right? They only open for a short period of time, though, and then there's pumps, and there's even chloride pumps, we haven't talked about them, that are going to reset the concentrations and take it back to resting potential. Those are your inputs. Okay? It's how a chemical signal gets turned into an electrical signal through the movement of those ions. Good? All right. So here's an EPSP. Sodium came in, channel closed, so it quit coming in. Pump's working, pumps it back out, back to resting potential. Now, if we have two multiple inputs coming in. What did Sherrington say? Do you remember Sherrington's experiments with the dog? He could pinch the dog and it wouldn't respond. It'd be below the threshold, but how could he get the dog to respond?
By doing the same like pressure but in two different places.
Yeah, but they had to be close.
They had to be close.
Close in space. We call it spatial summation. But what else could he do?
Multiple stimuli in the same area.
Yeah, do it real close in time, and they add it up, right? Well, that's what is happening here. If we have two of these that happen at the same time, they can add up, okay? So there's two ways that we get processing, and it's really complicated. It's not. It's addition. It's not calculus. It's adding. It's summation. And it happens when they are close in time, temporal, or close in space, same location. And these synaptic potentials are coming in all the dendrites and traveling down the dendrites, and where do all the dendrites end up? What part of the neuron do the dendrites end up at?
Soma.
The soma. That's where the processing happens. Okay? These are not exclusive. They can happen together. In fact, close in space, if they're close in space but they're not close in time, they won't add up. So they always have to kind of be, they have to be close enough in time. All right? When we say close in time, it means if I have one here and then another one here, if the pump has already pumped it back down to resting potential, there's nothing left to add to. That's why they have to be close in time. But if we have a second one here, and the pump hasn't pumped it back down, we can build upon that. All right? All right. The more we get, 3, the higher it goes. All right? Where are we going? Where are we starting?
-7.
-70. So we're going closer to 0. We're getting more positive. Right? All right. So they always have to happen within this window. The summation always has to happen before the pump can bring it back down. Otherwise, there's nothing left to add to. If it happens here, there's a little something to add to. If it happens here, we have the most to add to. Right? So we can have 3 action potentials, 3 signals in a row, and if they're close enough in time, they can add up. We can also have 3 close in space and time, right? You can't have this one and then it goes down, and then this one and it goes down, and then this one. That's not, you have to be in that window to add up. But close in space can also add up. Right. They can have it through one input or through multiple inputs. All right. So there's this line at -50. That's no marker. That seems like a magic number. Does anyone know what -50 is? The threshold. Yes. It's the threshold. And this is the yes in the decision making. If we get to -50, that's the decision the soma has to make. Do I send an action potential or not? Right? So, everything we've talked about so far, dendrites, soma, EPSPs, IPSPs, they have to summate in the soma. If you remember, I said that there's a very special part. Oops. Okay, sorry. Not there. Threshold. If we don't get to 50, what happens? Nothing. Okay? Yes? No. Okay? If we get to -49, what happens? Send an action potential. We get to -40, what happens? Same thing. right? It's either on or off, right? If we do cross that threshold, we get this huge potential. The inside of the neuron goes all the way up to positive 30. Use my marker. I don't want that marker. That's the peak of the action potential, right? And then it falls all the way down here to negative 75. So we have two phases of the action potential, a rising phase and a falling phase. These are important electrical potential numbers that you need to know. These are important channels, receptors that you need to know for synaptic. Okay? All right. So how do we get such a big change in the memory potential? We're going to talk about that next. This is just a summary slide. Write down slide 27. Dr. Piven didn't talk about it because this is summarizing everything he just said. But it's a good review for you to go look at, okay? And I'll post photos of the whiteboards after class as well. So. All right, do you know what time it is? We're halfway through. You don't have to get up. I got a special one today. Do you need your chair? I want to get your chair back. Absolutely.
All right, guys, ready for a jam in a minute? Let's get started. Sitting down in our chair, punch over our right shoulder. Go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Punch left. 10, 9, 8, 7, 6,
Get that glucose
5,
pumping.
4, 3, 2, 1. All right, lift up the right leg, climb underneath. Ready? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and left. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Grab on the chair, put your knees into your chest, kick out in. 10, 9, 8,
Yeah, it's an hour ago.
6, 5, 4, 3, 2, 1. Hang on to that chair.
All right, we're going to play.
Hold. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, great job, everybody.
All right, you're going to help yourself.
Okay, guys, your healthy sit for the day is read.
All right, so yes, make sure you're doing your reading. Okay. Everything we talked about so far are transmitter-gated channels. What opens the channel? Neurotransmitter. Thank you, man. Get pretty good at it. It's like y'all have been tricked and troubled. So it's all right. And all that's happening on the dendritic spines and the soma. Okay? Remember I said that there was an important part of the neuron between the axon and the soma? It's called the axon hillock. That's important because that is where we change from neurotransmitter-gated channels to voltage-gated channels. So if NT-gated channels opened by neurotransmitter, what do you think a voltage-gated channel is opened by? Voltage, right? All right. So, knowing what you know, what voltage do you think opens the sodium channel? What voltage is going to open the sodium channel? Negative 50. Threshold. Exactly. -50, what do you think is going to happen? Where does sodium want to go? Inside. In fact, so much sodium comes inside that we go from -50 all the way to what? +30. That's the rising phase. That's why I wrote it in red over there. Because that's due to so much sodium comes in that we go past 0, and now it's more positive inside the neuron than outside. When does the sodium channel close? At the peak, at +30. At +30. Again, that's the rising phase. All right. So much sodium has come in, because remember we have both electrical and concentration forcing sodium in. So much sodium comes in that this goes all the way to +30 inside. So what does that mean for potassium now? It still wants to leave because we haven't let any out, right? Concentration-wise, but what happens electrically now? Does potassium still want to stay inside based on electricity?
No, it needs to go out.
Because it's positive now. So this actually reverses, and at the top of the action potential, potassium now really wants to get out of the neuron. And so at -40, just after sodium opens, potassium opens, but potassium stays open for a longer period of time. So once sodium closes, potassium is leaving, and that brings the charge. This is potassium exiting all the way back down here to -75. We call that the falling phase. All right? Sodium coming in, potassium leaving. All right. This is just another diagram of that, right? We have sodium coming in, it closes now, starts to fall, potassium exiting, and then it comes back to normal. All right. The sodium opens first, closes at the top. Potassium opens at -40 as it's on its way up, stays open longer, closes when it gets to -75.
Quick question. On the previous slide, it said something about -70 MV. What is that again?
Resting potential. But now we're below resting potential after an action potential. All right. Okay. So, if this is our axon, again, my fancy drawing of a tube, here's axon hillock. Synaptic potentials, EPSPs and IPSPs, summate and reach that -50. So what happens right here? If it gets to -50 in the soma, what happens right at axon hillock? Yeah, what happens? Yeah. And so what happens to start it?
It reaches the threshold.
Yes. And what happens?
The NA, does it open?
It opens and sodium comes in. So much sodium comes in now that we get positive. And then potassium opens and potassium leaves and we get our falling phase. Okay? And then what's happened? We put all the sodium inside the neuron, all the potassium outside. If we want to have another signal, what do we have to do? Get it back to normal. And what gets it back to normal? The pump. This is why neurons use a lot of energy. We have to pump the sodium back out and pull the potassium back in so we can reestablish the forces so we can send another action potential. During this time that we haven't restored the forces, if the sodium channel opens, what's going to happen? If we get another threshold and the sodium channel opens, if we haven't put the sodium back outside, it opens and nothing moves because there's no force. We haven't put it back out. So this is a period in which we can't have another action potential. It's called the refractory period. Refractory period. No action potentials in the refractory period. All right. Okay, so does anyone know how we kill people by lethal injection?
Potassium, to cellular.
Yes. So there are 3 injections that the person who's being executed gets. The first one is a sedative, because we don't want them to be upset that they're killing them, right? So we give them a sedative so that they're not as aware of what's going on. And then the second one is a muscle paralyzer, because we don't want them to spasm and we don't want it to look bad when we kill them, right? So we paralyze them. Now, effectively, that person's going to die now because they're going to suffocate eventually because they're not breathing anymore. So we paralyze them. But that's not a very humane way to kill people. So the third injection, the thing that kills them, is a big injection of potassium. So we put so much potassium in, extracellularly, right, that all neural signaling stops because there's no, when that channel opens, we don't have a falling phase. A rising phase, and there's nothing to bring it back down. So now you know. All right. Here's another diagram sort of showing all this stuff happening. Notice here, what's the threshold? Is that threshold? What's threshold? For us, it's -50. Now, remember I told you last week that if I say always, it means usually in here? So there are neurons. There are some neurons that have different thresholds, like -65. So this is not incorrect, per se. But for us, in your narrative and your exam material, these are the voltages that we are focusing on, right? This goes up to what? Up to 40 instead of 30. So I show you this just so you know that you might see some different voltages, but the process is the same, the channels are the same, the numbers are just slightly different. But we're going to focus on these numbers as our standard numbers. That's what's really recognized as the standard. Okay? All right. Axon hillock, action potential, right? That voltage moves down to the next channel, and as long as this big positive signal, positive ions inside go down here, activate this one, in, out, action potential, activate down here, in, out, action potential. And behind this, we're in the refractory period. Nothing can happen, haven't restored the forces. Pumps work. Pumps work. Now we've restored forces. If we want to send another signal, it's ready to go. Not ready to go, refractory period, already restored back here, ready to go. Signals moving down the axon to the axon terminal. A lot of work for those pumps, a lot of energy, right? All right, so what was missing, what's missing from that neuron? Oh, sound effects. Okay. We had our action potential. It's being regenerated. Remember, we said we only need a very, very small electrical signal because we're going to regenerate it. It doesn't have to be a big signal that starts here and has to go all the way to here because we're going to regenerate. But what's missing from the axon? Matt, what's your question?
Myelin sheath.
Myelin sheath, which does what? Insulates. It makes it more efficient. So we only have to regenerate at these breaks called nodes of Ranvier, because of the French guy who discovered it. And so here, if we were to have a potential here, and then we record that, it's going to dissipate, right? It's going to get smaller the further away we get from where it occurred. It's biggest right here, and then it kind of dissipates. It's weaker. If, however, we slap some myelin on there and trap those sodium ions and don't let them dissipate, now, instead of it being this small down here, it's big enough to allow these sodium channels to open, voltage-gated channels to open, and regenerate it here at each node along the way. So there's no pumps and no channels in this section. We only have to put those energy-using things at the nodes. Okay? So it's like we're trapping that signal and regenerating it and moving it on down. Good? All right. This sort of jumping, we call it saltatory conduction. You can think of that as, okay, salts, sodium and potassium are what are causing this. That's not why it's called that. It's called saltatory because saltatory means jumping or skipping down the axon. So we have a very low level signal that gets boosted in between myelin, which is insulating, so we can send that electrical signal really fast down the axon. All right, here's another picture kind of showing this, how the voltage gets trapped in the myelin down to the next node and then regenerated there. I like this one the best. So here we see at the start of the action potential, sodium comes in, it goes all the way to positive 30. Way down here, what's the potential? Negative 70. Nothing's happening way down here, right? If so much sodium comes in, then as long as those positive charges reach negative 50 here, what's going to happen here? It's going to do it again, right? So it's doing it again here. Behind, remember potassium is the falling phase, it lags a little bit behind the sodium. Potassium is leaving, so now we're at positive 30 here, we're coming down to our negative 75. Pumps are working to fix the concentrations. Now it's coming down here, but we've moved on down to here, and you can see how it does that saltatory conduction down the axis. Sodium, when sodium floods in here, it's a little bit misrepresented. I wish that they had drawn this a little differently. It doesn't just go this direction, right? It comes in and goes like this, right? But why doesn't it have an effect back here? Why does it only have an effect in that way? Because we're in a refractory period, right? Because there's nothing, because the potassium is leaving. Right? So that drives it in one direction. One direction. So the timing of that's important to keep it moving in the right direction. All right. What happens if we have a disease like multiple sclerosis where the immune system attacks myelin and removes it? The action potential won't reach the next node. It can't be regenerated. And so we have issues, difficulty with sending signals. And that's what's happening with MS. If that happens in the periphery, it can result in numbness or loss of sensation if it's a sensory neuron. It can result in weakness or paralysis if it's a motor neuron. If it happens in the brain, it results in problems with parts of the brain communicating with each other. Wow. We do have some neurons that are unmyelinated. So if we have a neuron that's unmyelinated, what does that mean? What's the effect of not having myelin going to be? Is it going to use more energy? We're going to have to regenerate that signal all the way along the axon if we don't have insulation, right? So we're using a lot more energy, more pumps, and by the time this neuron that's myelinated has regenerated it twice, look how far it's traveled. By this time it's regenerated twice, look how far this has traveled. So what does that mean about the speed? A lot slower than myelinated. All right. Have you ever been hanging a picture or working with a hammer and a nail and you hit your thumb with the hammer? Has anyone ever done that? What happens when you do that? How does it feel? It hurts. It hurts. There's like, when you crush your thumb, it's a big, immediate pain signal. And then what happens? So you get that sharp, immediate pain.
Like a throbbing.
And then there's this numb, throbbing soreness that happens, right? When you hit your thumb, a myelinated signal is sent. That's the sharp, immediate pain. But the pain system uses unmyelinated neurons to produce that long, slower, prolonged throbbing pain. So next time, see, I'm going to give you all this information that's going to sort of make you geeky. So next time that you crush your finger or drop a book on your toe or something like that, you're going to think, oh, that's the myelinated signal. Wait for it. I can tell how long it's going to take. Oh, now the unmyelinated signal is reaching, right? You can actually tell the difference in speed between myelinated and unmyelinated when that happens. And that's pretty much one of the only places, again, usually, that we find unmyelinated is in the pain system. And we'll talk about that more when we get to the sensory systems in the next section. All right. Weird. Good. All right, so summing this up, action potentials. It's all or nothing. What is it based on? We call action potentials all or nothing. On or off. What makes the decision?
Whether we reach the threshold or not.
Whether or not inputs, EPSBs, summate enough to open that first voltage-gated channel at -50. If that happens, it's like a gun that goes off and you pull the trigger and there's no going backwards. Action potentials will happen. Unless we have a faulty neuron that doesn't have myelin, that could stop it, right? But if given everything's normal and healthy, as soon as we get that first threshold, that -50 opens, it's set up to go. All action potentials are identical. They can't be bigger, smaller, faster, slower, because all of this happens the same way each time. It doesn't matter if our input gets to -49 or -40, because it stops. That input doesn't matter once it opens that -50 voltage-gated channel. All right, myelin allows the saltatory conduction, the jumping, right? Saltatory conduction allows to regenerate the signal, to have a low voltage, and to only regenerate it at certain places to increase the efficiency, to decrease the number of pumps and channels that are working, to get it through them. All right, questions? We've gone through synaptic and action potentials. All right, don't get excited, but that was what I planned for today. But I'd like to work a couple slides forward into the next lecture just in case. We have time. It's going to be good. This is awesome. This never happens. All right. So EPSPs, IPSPs, through neurotransmitter-gated channels, the signals go down the dendrites into the soma. If they add up in time and space, temporal and spatial summation, and reach -50 at the first voltage-gated channel, we're going to get our action potential that goes all the way down here to what? Axon terminals, and we get neurotransmitter release. So that's a part of this whole process we haven't talked about yet. Okay? All right. These are just pictures of things that I'll show you. So I'll probably go back over that. I'll go back over that next on Thursday just as a review. But just to add to this, this is happening in dendrites and soma. And this is happening axon and the terminals. All right. There's another voltage-gated channel that we haven't talked about yet that involves calcium. So neurotransmitters, remember, those chemicals, they're stored in bubbles, vesicles, and they're down here waiting for a signal to be released. What's the signal that's going to release them? What signal is going to cause them to be released? What do you think? It is the action potential. That's the yes or no signal. Are we going to send a signal to the next neuron or not? All right. So the action potential reaches the terminal, allows neurotransmitters to be released. They go across the synapse, bind to what?
Receptors.
To what?
Receptors.
Neurotransmitter-gated receptors, and the process can start again in the next neuron, right? They only bind for a short period of time, and then we want to get rid of the neurotransmitter because if we want to send another signal, we need to know that that's a new signal versus the old one. So we have to remove the neurotransmitter out of the synapse. And that happens in 3 different ways we'll talk about. All right, so this is the last thing I want to cover today, is getting neurotransmitter out of the terminal. How does this action potential cause the neurotransmitter to be released? So it turns out, if we have these 2 neurons, again, a culture prep, where we might have neurons in a dish, and we know this neuron is connected to this neuron, and we can measure the electricity here, and we can do things to this neuron, like have an action potential that we're measuring, we get neurotransmitter release, and then we get an action potential over here, right? If we put a little needle in here and say, hey, what's going on inside the terminal when that happens? It turns out there's a high amount of calcium. A high amount of calcium. And it turns out if we come in and we have no action potential here, but we just inject calcium into here, what do you think will happen? It releases neurotransmitter, and we get action potentials in the next one, even though there was no action potential here. Now, what if we take those neurons in that bath, and we want to know, okay, well, if calcium is responsible for causing neurotransmitter release, where does it come from? What if we put no calcium outside this cell, and we have an action potential that comes along? What do you think will happen? What do you think will happen? If our hypothesis is that calcium comes in and causes neurotransmitter release and we don't have any to come in, nothing's going to happen over here, right? Get no neurotransmitter release. In fact, that's what happens, right? So calcium is required in that extracellular fluid. So it turns out there's another voltage-gated channel here at the axon terminal, a calcium channel. And when that big voltage of the action potential reaches the terminal, it opens the calcium channel and allows calcium to come in. And that calcium is the signal to the vesicles to release their neurotransmitter. Exocytosis, exiting the cell. It's an influx of calcium. All right. And this happens in kind of a two-step process. First, the vesicle full of the neurotransmitter, cell membrane of the axon terminal, right? The vesicle gets docked or bound to the cell membrane, waiting for the calcium signal through a bunch of different proteins that you don't need to know the names of, but I do want you to know they're called the snare complex, because that's easy to remember. The snare complex snares the vesicle and holds it docked and ready to go. Good? Now, here's the protein that you do need to understand. When calcium comes in, the calcium ions activate a protein called synaptotagmin. So think about synapse and tag you're it. We're going to release the neurotransmitter, right? Synaptotagmin. And that fuses those cell membranes of the vesicle and the cell membrane to allow the neurotransmitter to go out. Because remember, what is this? The cell membrane? Plasma, right? We can open it up and allow it to close back up. And that's the job of synaptotagmin. Synaptotagmin only does that when calcium is present. Calcium is only present when the action potential opens those voltage-gated channels. Yes, Sam?
So the vesicles are made out of the membrane?
Yes, vesicles are also like have a cell membrane. So they just pinch them together. They just fuse together, dumps it out, and then this thing called dynamine comes along and pinches it off, and we can recycle. Neurons are all about recycling. All right. I'm going to stop there. You gave me 10 extra minutes. I'm going to give you 10 extra minutes. I did have a question, ERP, right? And if anyone else has questions, I'm happy to answer them. But Kathleen asked me to explain ERP a little bit better, and I said I'd do it at the start of class, and I forgot. So the EEG that you did, right? That signal was all random looking, right? And that was good, right? If it wasn't, that wasn't a good signal when you did your EEG. So an ERP is where you have a bunch of stimuli presented over and over and over, like maybe 100 times, and you take an average, all of the EEGs, right when that stimulus happened. And when you do that, it kind of removes the randomness, and you get a curve that has particular excitatory and inhibitory parts of it that are related to the brain activity in response to that stimulus. So if any of you were in there doing your data and you heard the beeping, did y'all hear the beeping in the room next to you? Anyone? That's an experiment in cognitive psychology where they're doing an ERP. And every time they have two tones, they have this one lower tone and one higher pitched tone that only happens intermittently. And so they're recording their brain activity in response to those tones. And it turns out that when you have the different tone that happens intermittently, you get a change in that ERP shape in response to the unusual stimulus, right? So that's what they were doing. That's why you heard all those tones over and over again, because they're going to average the EEG right after each of those tones across all those trials. Did I explain it? So event-related potential, ERP. The event is the stimulus that's produced over and over. The potential related to that is what we measure. Any other questions? All right, stay safe. Wednesday, 2 o'clock, in the neuroscience lab, which is the end of the hall on the left side, 228, sheep brain neuroanatomy. If you want to get ahead, the video is already on there. You can start learning some stuff, but you don't have to. I'll teach it to you in lab. You will have a lab practical at the end of the lab for those structures. So the goal is to learn them during the lab and then take the lab practical at the end of the lab.